So picture this. You are driving past this perfectly green, sprawling orchard, right? And it's in the middle of just a bone-dry summer.
Oh, yeah. Classic summer road trip scenery.
Exactly. And, millions of gallons of water are just pumping through those fields, creating this totally lush oasis in the heat. It's a stunning visual, but, there is this razor-thin margin of error hiding behind all that greenery.
A terrifyingly thin margin, honestly.
Right, because if the people running that farm overwater their crops by, just a fraction, they're wasting our most precious, finite global resource. And they literally rot the roots of their own plants.
Yeah, which is a disaster.
But if they underwater, the crop suffocates, the yield crashes, and, well, the farm goes bankrupt. It's an incredibly high-stakes game. So how do they know the exact drop to use?
Well, people often assume there is, a lot of guesswork involved.
Oh, for sure. You just picture like a seasoned farmer looking up at the clouds.
Right, kicking the dry dirt with a heavy boot and just using gut instinct to turn the irrigation pumps on.
Yeah, exactly.
Yeah. And, while experience is obviously invaluable, when you are operating at an industrial scale to feed the planet, intuition simply does not cut it. We are looking at a system designed to maximize economic yield under the strict, unforgiving mandate of biological reality.
Which means it is a rigorous, deeply calculated science. And that is exactly what we're getting into today. For this deep dive, we're exploring this framework used by agronomists and irrigation designers called the crop coefficient approach.
Yes, the crop coefficient. It's brilliant.
And we've got some amazing source material for this. We're looking at a fascinating set of university lecture notes for a course called AGPS 301 Irrigation Design and Management.
A really comprehensive set of notes, yeah.
Yeah, and the mission here, our goal for this deep dive, is to just demystify this complex mathematical and environmental balancing act that dictates crop survival. We're going to decode how experts calculate the exact amount of water a plant needs to produce a yield without wasting a single drop.
It's so important, too, because the core value of this knowledge isn't just about farming, It's about critical resource management in a world of just massive variables.
Right. Okay, let's unpack this, because before we can even talk about, how much water a field of corn or a cucumber vine needs, we have to talk about the atmosphere.
The invisible sponge.
Exactly. The sky itself acts like a giant invisible sponge. And to understand that sponge, we have to look at a concept called evapotranspiration.
Right, evapotranspiration. It's one of those massive, intimidating scientific terms that actually makes perfect sense when you break it down.
It's really just two words smashed together, right?
Exactly. Evaporation and transpiration. Both processes are happening simultaneously in any given agricultural field, and they both result in water leaving the earth and returning to the atmosphere as vapor.
I think most of us have a solid grasp on the evaporation part. The sun beats down on the wet soil, the thermal energy heats up the dirt, and the moisture on the surface just turns into vapor and drifts away.
Yeah, it's a purely physical process. But plants are not just inert objects sitting on top of the dirt. They're active, incredibly complex biological machines. And that brings us to the second half of the word, which is transpiration.
Okay, so how does that part work?
Well, a plant draws liquid water up from the soil through its root system, and that water travels up through the vascular tissue of the plant, the xylem distributing nutrients. But eventually, that water reaches the leaves.
Yeah.
And on the underside of those leaves are thousands of these microscopic pores called stomata.
Wait, so the water literally exits the plant through those tiny pores?
It does, yeah. The plant opens its stomata to take in carbon dioxide from the air, right? So it can perform photosynthesis.
Oh, I see.
But the moment it opens those microscopic doors, the moisture inside the leaf is exposed to the dry atmosphere outside, and the water vapor just escapes.
Wow, so it's like an unavoidable trade-off.
Exactly. It is the biological cost of doing business. Together, the evaporation from the hot soil and the transpiration from the living plant make up the total water loss from that specific area. That is evapotranspiration.
The invisible sponge soaking up the moisture.
You got it.
And to figure out how much water a farmer needs to pump back into a field, you first have to figure out just how thirsty that invisible sponge is on any given day.
Yes.
And to do that, you need a baseline. Agronomists call this baseline the reference crop evapotranspiration, or ETO.
Right, because you need a standard unit of measurement. The atmosphere's thirst is just wildly volatile.
Right, it changes every day.
Yeah, you cannot just look at a thermometer and say, well, it's 90 degrees today, so the air wants a lot of water.
Yeah.
Humidity, wind speed, solar radiation, They all change the pulling power of the atmosphere.
So scientists had to establish a universal reference point.
Exactly. When they talk about ETO, they are talking about the exact rate of evapotranspiration from a very specific, perfectly controlled hypothetical field.
And wait, looking into this standard in the AGPS 301 notes, the reference point is a giant patch of grass.
A very specific patch of grass.
Yeah, not just any grass. It has to be exactly 8 to 15 centimeters tall. It has to be actively growing, completely shading the ground beneath it, and it cannot be short of water in any way.
It's the platonic ideal of a suburban lawn.
It really is.
Yeah.
But, I mean, if I'm a commercial farmer growing miles of wheat or, I don't know, acres of apple trees, why do I care about a perfectly manicured lawn?
Because you need a control subject that never changes its behavior.
Okay.
If you use wheat as your glass line, well, wheat changes dramatically from a tiny sprout to a towering dry stalk.
Right, of course.
But grass, properly maintained at that 8 to 15 centimeter height, offers a consistent aerodynamic roughness. It creates a uniform surface for the wind to blow across. It provides a constant amount of shade to the soil.
So it locks the variables in place.
Precisely. By locking the biological variables in place, the only thing left to dictate the water loss is the climate itself.
So it makes so much sense.
Yeah, so if that perfect patch of grass loses 1 or 2 millimeters of water a day in a cool, humid climate, but loses 9 or 10 millimeters in a dry desert over 25 degrees Celsius, you now have a hard mathematical metric.
You know exactly how aggressively the local atmosphere is pulling moisture.
Yes, exactly.
So is ETO essentially like establishing a basal metabolic rate for a perfectly average human athlete, just so we have a standard to compare all the other athletes to?
That is a phenomenal way to look at it, yeah.
Oh, cool.
If you're a sports nutritionist and you want to know how many calories an Olympic swimmer burns during a race versus, say, a gymnast on the rings.
You first have to know what a completely average baseline human burns just standing still.
Exactly. That 8 to 15 centimeter grass is our average human standing perfectly still in a room.
But how do they actually measure the water evaporating off this hypothetical grass? I mean, you can't put a giant glass dome over a field and catch all the invisible vapor.
Well, you calculate it. And today, we often use extremely complex algorithms fed by weather station data. But before we had instantaneous satellite data, and honestly, even still today in many parts of the world, there is a highly physical, brilliantly analog method to measure this atmospheric demand.
The Class A evaporation pan.
The Class A pan.
I became absolutely fascinated by this metal pan in the source material. It sounds so rudimentary at first glance. It is literally a tub of water sitting outside. But it is engineered to an absurd degree.
Oh, the engineering is wild.
It's a circular, galvanized metal pan, exactly 120.7 centimeters wide.
Yep.
It's exactly 25 centimeters deep. You fill it with exactly 20 centimeters of water. And you don't just leave it on the dirt. You have to place it on a very specific 5-centimeter tall slatted wooden pallet.
What's fascinating here is the meticulous, almost obsessive design behind every single one of those dimensions.
Right. Why the pallet?
Take the wooden pallet, for instance. It isn't just to keep the pan clean. It allows air to circulate underneath the metal bottom.
Oh, I hadn't thought of that.
Yeah, if you place that metal pan directly onto the bare earth, the soil would act as a massive thermal battery. It would soak up the sun's heat all day and then slowly transfer that heat into the metal pan all night.
Which would artificially warm the water.
Exactly, causing it to evaporate faster than it should. The pallet isolates the water, ensuring its temperature is dictated purely by the ambient air and the sun, giving you an accurate reading of the atmosphere's true thirst.
So the farmer walks out to this wooden pallet every single morning, let's say at exactly 7:00 a.m., with a specialized ruler.
Right.
And if the water was sitting at 20 centimeters yesterday, and today it is at 19 centimeters, you know you have had 10 millimeters of physical water loss. The atmosphere drank 10 millimeters out of the pan.
That's EPAN.
Okay, EPAN, but I know enough about science to know I can't just look at a tub of water and say, well, the tub lost 10 millimeters, so my living grass must have lost 10 millimeters too.
No, you hit the nail on the head. Biology does not behave like galvanized metal. A metal pan heats up much faster than a green leaf. It reflects sunlight differently. It doesn't have a vascular system, and it certainly doesn't have stomata regulating its moisture loss.
It's just open water.
Exactly. A pan of open water is entirely at the mercy of the elements. Therefore, you have to apply a conversion rate to translate the pan's water loss into our grass baseline.
Okay, and this is the pan coefficient, or Kpan.
Yes, Kpan.
So you multiply the pan's physical water loss by this coefficient, to get the true biological grass baseline.
And that coefficient fluctuates wildly based on the reality of where your pan is sitting.
Like the surrounding environment.
Yeah. If your pan is in the middle of a dry, barren, fallow field, the wind whipping across that hot dirt is going to pull moisture out of your pan violently.
Oh, right.
It will evaporate much faster than a lush green field of grass would. So your coefficient has to aggressively correct for that localized extreme.
Okay, so we have done it. We've used our highly specific pan, we've applied our coefficient to correct for the metal, and we now know exactly how much water the climate is sucking out of our hypothetical 15-centimeter grass.
We have our basal metabolic rate.
Exactly. But a farmer's field isn't filled with control subject grass. They are growing enormous stalks of corn, sprawling cucumber vines, and dense cotton plants.
Which means we have to decouple the climate's demand from the specific plant's identity.
Okay.
Because knowing the climate's thirst doesn't help us if we don't know who is doing the drinking. Enter the crop coefficient.
The KD.
Yes, Casey.
So this takes our formula and evolves it. Now we take our grass baseline, the E2O, and we multiply it by the specific crop coefficient.
And that final number is ET crop, the actual real-world water requirement for the specific plant you are trying to keep alive.
It's a brilliant scientific separation, honestly.
It really is. By establishing the climate demand first, we isolate the plant's identity into this single number, the KSI. And because we isolated it, we can take that plant's identity and use it anywhere in the world.
Oh, wow.
Yeah, the physiological nature of a maize plant, its cellular structure, does not change just because you move the seed from an Ohio farm to a field in South Africa. Only the baseline climate demand changes.
That's incredible. And the differences in these plant identities are massive, too. The notes mention that a fully developed maize plant has these massive, broad, towering leaves, so its crop coefficient is greater than 1,
Right.
meaning it requires significantly more water than our perfectly watered baseline grass.
Yes.
But a fully developed cucumber has a crop coefficient of less than 1. It actually needs less water than the grass. Wait, let me push back on the mechanics here for a second.
Sure.
If maize uses more water than our standard grass, simply because of its large leaves, does that mean the plant is literally sweating more?
Well, in a biological sense, yes, though the mechanics are really tied to the physics of leaf surface area. Think back to those microscopic stomata we talked about. Every square inch of a leaf contains thousands of those pores. The more surface area a plant has exposed to the sun and the whipping wind, the more pores it has open to the atmosphere.
So it's just physically losing more vapor.
Exactly. A maize plant is effectively a massive solar sail. It is genetically designed to capture huge amounts of light to drive incredibly rapid, aggressive growth.
Right.
But the unavoidable trade-off for building a solar panel that big is that you have a massive surface area bleeding moisture into the dry air.
Wow, okay. And the cucumber?
A cucumber vine, by contrast, stays low to the ground. Its leaves shade each other, creating this humid microclimate right at the soil level, which actually suppresses transpiration. It has a completely different architectural strategy for managing its internal water pressure.
That makes total sense. You build a bigger biological solar panel, you need a bigger hydraulic cooling system.
That's exactly it.
But a corn plant isn't born as a massive solar sail. I mean, when you first put the seed in the dirt, there is no leaf surface area at all. It is just bare ground.
Right, which means the thirst of a plant is not a fixed static number. It's a highly dynamic timeline. The crop coefficient changes constantly based on the plant's biological growth stage.
And the AGPS notes divide this timeline into 4 distinct chapters.
Yes, 4 stages.
First, you have the initial stage, which is right after planting. Then you move into crop development, where the green shoots start rapidly expanding and covering the dirt.
Right.
Then comes the mid-season, which is when the plant is fully mature, towering in the field, firing on all cylinders. And finally, the late season, where the crop is ripening, drying out, and getting ready for harvest.
If you plot this on a graph, the Kamic curve tells a very vivid story of the plant's life.
Okay, how so?
Well, during that initial stage, the crop coefficient is incredibly low. The plant is barely a speck of green. So the vast majority of the evapotranspiration happening in that field isn't transpiration at all. It's just raw evaporation from the exposed wet soil.
Oh, because the sun is just hitting the dirt directly.
Exactly. But as we transition into crop development, that line ramps up aggressively. The leaves are spreading out, casting shade over the dirt, which shuts down soil evaporation, and plant transpiration takes over as the dominant force of water loss.
Here's where it gets really interesting, though. the mid-season.
Oh, yeah.
This is the peak of the mountain. You look at things like sugarcane, cotton, maize, cabbage, onions, apples. When these specific crops hit their mid-season stride, their crop coefficient plateaus around 1.2.
Which is massive.
Right. They're actively consuming 20% more water than our perfectly watered reference grass.
They are absolute water engines during this phase. They require massive internal hydraulic pressure to achieve their evolutionary goal.
Which is producing the food, right?
Yeah, they're setting grain, producing sugary fruit, and building the heavy economic yield the farmer is banking on. Their stomata are wide open, pulling in carbon dioxide and just bleeding out vapor.
But then they hit the late season and the curve just drops off a cliff.
It really does.
And this naturally makes you wonder, when that water demand plummets in the late season, does the plant magically know to stop drinking? Like, does the corn stalk send a signal saying, hey, the ears are full, shut off the internal valves? Or is it just the physical reality of the plant turning brittle and drying out as it dies?
It is less of a conscious decision and more of a deeply programmed biological shutdown. It's a process called senescence.
Senescence, yeah.
The plant has achieved its purpose, right? It has produced viable seeds for the next generation. At this point, maintaining those massive solar sails is just a waste of energy.
So it just shuts them down.
It literally begins to dismantle its own cellular machinery. It breaks down its chlorophyll, which is why the leaves turn from deep green to yellow and brown. The stomata becomes sluggish and less responsive, and the vascular system that pulls water from the roots begins to collapse. Its physical machinery for transpiring water is actively degrading.
And the climate dictates the speed of this entire biological clock, right?
Yes, absolutely.
Because a crop growing in a cool, cloudy climate develops much slower than that same crop in a blistering, warm climate. You can't just put it on a calendar and say, maize takes exactly 40 days to reach peak thirst.
No, you have to adjust the duration of these stages based on the ambient heat of where you are on the planet.
Right.
And if we connect this to the bigger picture, it becomes clear that farmers are fighting a multi-front war.
Oh, for sure.
They are managing the climate-shifting thirst. They are tracking a constantly moving biological clock. And unfortunately, the math we've discussed so far assumes a completely perfect, frictionless world.
Which doesn't exist.
Exactly. Fields are not sterile laboratories. We have to introduce a stark reality check here. The concept of ET adjusted.
Real-world chaos.
Yes, chaos.
Because even if you calculate the basal metabolic rate perfectly and you track the crop coefficient flawlessly, a dozen physical factors can completely wreck your pristine math.
Oh, easily.
Take soil salinity, for example. The notes say if there's too much salt concentrated in the dirt, the plant's water requirement fundamentally changes.
Yeah, and we have to look at the mechanism there. Why does salt matter? It comes down to osmotic pressure.
So break that down for me.
Well, water naturally wants to move from an area of low salt concentration to an area of high salt concentration. Usually, the plant's roots have a higher concentration of solutes than the wet soil, so water flows easily into the roots. But if the soil is packed with salt, that osmotic pressure reverses.
Oh, wow. So the dirt is trying to pull the water out of the plant.
Basically, yeah. The plant has to expend massive amounts of its own metabolic energy just to pull water away from the salty dirt. It stresses the plant, forcing it to close its stomata to conserve internal moisture, which obviously plummets its transpiration rate.
The same chaos applies to pests and diseases, right?
Absolutely.
If an insect swarm descends on your field and eats half the leaves off your maize plants, your biological solar panels are suddenly gone.
They're just gone.
The surface area vanishes, and your precisely calculated crop coefficient drops unexpectedly. Even the specific type of irrigation system you install alters the math.
Oh, profoundly. Consider the physics of delivery. If you use massive overhead sprinklers, you are throwing water violently through the dry air.
Yeah, you see this all the time.
Right. But a significant percentage of that water is going to evaporate into the atmosphere before it ever touches a leaf or the dirt. Your system is inherently inefficient.
Contrast that with drip irrigation.
Exactly. With drip irrigation, a tube delivers a slow, steady trickle of water directly into the soil at the base of the root zone, virtually eliminating surface evaporation. Every one of these chaotic variables adjusts the final, real-world rate of water loss.
Which brings us to the culmination of all this science, the final math.
The big equation.
We have the climate's baseline demand, we have the plant's unique identity, we are tracking its life stage. And we have factored in the chaos of salt, bugs, and sprinklers. Now, the ultimate question, how much water do we actually spray onto the field today?
The ultimate formula for survival. The crop's total water requirement minus the effective precipitation from the sky equals your exact irrigation requirement.
Put simply, what does the plant physically need to survive today, minus the free water the clouds gave us yesterday, equals what the farmer has to pump out of their own reserves?
That's the formula.
To visualize this, let's walk through a conceptual scenario without getting bogged down in decimal points. There's actually an assignment in the AGPS 301 notes due May 16th, 2025 that outlines this perfectly.
Oh, I love a practical example.
Let's say you have a field of maize, and it has hit that mid-season peak. It is firing on all cylinders, demanding 20% more water than our baseline grass. So its KCs is 1.2.
Right, so we have established the identity and the timeline.
Next, you walk out to your Class A evaporation pan. You measure the water level, and the metal pan tells you that 12 millimeters of water evaporated over the last 24 hours.
Okay.
You apply your conversion coefficient. Let's say Kpan is 0.8 to correct for the metal, scaling that number back to get the true biological baseline. Then, you multiply that baseline by the maize plant's massive thirst factor of 1.2.
Now you have a hard, irrefutable number. You know exactly what the maize field demanded from the soil yesterday.
Then, you look at the rain gauge. Let's say a brief storm rolled through and gave you 6 millimeters of effective precipitation-free rain that actually soaked into the root zone.
Right, effective precipitation is key there.
You subtract that free rain from the massive demand of the maize plant. The number you are left with is the deficit. That is the exact amount of moisture the field lost.
And you check that deficit against the water currently stored in the soil. The dirt itself acts like a biological battery, holding on to moisture. The notes give a readily available water value of 11.04 millimeters in this scenario.
Oh, okay.
So if yesterday's deficit drains that soil battery dangerously close to zero, you have to turn the irrigation pumps on immediately to fill it back up. If the soil battery still has plenty of charge, you wait.
So managing irrigation is essentially like balancing a highly volatile checkbook.
That is exactly what it is.
The blazing sun and the growing plant are constantly making these aggressive daily withdrawals from the account. The rain makes occasional, totally unpredictable deposits. And the farmer is the stressed-out accountant, having to write a check from the storage tank every single day to cover the exact difference so the account never, ever hits zero.
This raises an important question for anyone listening.
Yeah.
How confident would you feel managing this biological bank account every day?
I would be terrified.
Right, because a miscalculation here doesn't just mean a minor overdraft fee. If you overwater, you flush expensive fertilizers deep into the earth where the roots can't reach them, you suffocate the plant by drowning the oxygen out of the soil, and you waste incredibly precious fresh water.
Yeah.
But if you underwater, you stunt the growth, the yield collapses, and the farm fails. The precision we are talking about isn't an academic luxury. It is the absolute foundation of agricultural survival.
It really changes how you look at a sprinkler rhythmically ticking back and forth across a field.
It really does.
We have covered a massive amount of ground today. We started with the sheer physical forces of evapotranspiration, learning how the climate acts like an invisible moisture-stealing sponge.
We did.
We explored the absurdly precise engineering of the Class A pan and the necessity of establishing a 15-centimeter grass baseline.
Then we moved into the vascular biology of the plant, decoupling the climate's thirst from the crop's identity using the crop coefficient.
Right.
We traced that thirst across the 4 distinct chapters of a plant's life, and we learned how salt, pests, and delivery methods throw chaos into the equation.
And finally, we brought it all together, balancing the daily biological checkbook against the rainfall to find the exact, perfect irrigation requirement. That simple sprinkler running in a field is actually the physical manifestation of deep, precise meteorological and biological calculations. So what does this all mean?
Well, I think the most important takeaway is this. The mathematics and the biology we just explored outline a flawless system for achieving optimal growth with absolute zero waste.
Yeah.
We have the scientific capability to perfectly match a crop's thirst to the climate's demand. But knowing this, I want you to consider the global reality.
Okay.
Consider how much of the world's fresh water, our most precious, rapidly depleting resource, is likely being wasted right now, at this very second, simply because these precise scientific principles are not being universally applied, and people are still just guessing when to turn the water on.
That is a staggering thought and perfect place to leave it. Thank you so much for joining us on this deep dive. Next time you look out at a massive industrial farm, or honestly, even just the potted cucumber plant sitting on your back porch, I hope you see the invisible mathematical exchange of water, vapor, and life happening right in front of you. Catch you next time.